Okay, as you see, in my talk I'm going to cover a lot of topics here, and because I only have 20 minutes for the whole talk and also those musician bells in the back, I don't go too very much into detail, but I think all those topics are new or at least interesting for you. And I will start with an update of the hardware. So I picked a few things here, like the helium saver. In the middle part, I want to say something about the software. This time I want to say something about the DFS software itself. And finally, I want to give you an update about our project called Timed Cryogenic Zoom Compression. Okay, so the DFS is now delivered with a new GC. You probably have seen it before. It has a lot of new developments integrated here, like it can cool down very fast. But one of the major features here is the module design of the injectors and also the detectors. So you as a customer can on the fly change or upgrade the system to other injectors or detectors. And in this context, I just want to show you a new module which is available now. It's called the helium saver. It's done in a module which is installed opposite to your injector here, and with that module you only use helium when you really need helium, and all the rest of the time, and also septum purge and those things are done with cheaper gases in the meantime, and by that you save a lot of helium, and helium becomes more and more expensive, and with that I think this module will pay off very quickly if you use it. They say in perfect condition, one single helium cylinder should last 14 years. I ordered this one, I haven't tested it yet, so in the next Pop Symposium 2028, maybe I know if this is true or not. So another module which is available is for all the people who have to change the column on a regular basis, because with that module here, the so-called no vent, you can change it or open the connection to the analytical column without breaking the vacuum of the mass spec itself. So that saves time and also some trouble, because afterwards you have to retune, you have to cool down the source, and that's time consuming. Now to the DFS, I want to say something about flexibility, and I'm not talking about the DFS itself is a very flexible instrument. It has a different ionization mode like CI, FAP, FI, different inlet system, DI, DCI, Lifty. We did a lot of Lifty experiments for oil industry in the last weeks, and also different experiments what you can do. Here I'm just talking about flexibility in connection with the GC. Only the fact that you can hook up two GCs at the same instrument already gives you a lot of flexibility. But if you combine this with this dual column adapter here, you can install two columns in one GC. And an application what I have on mind here is for brominated. For example, everybody knows that the DECA, the 209 BDE, is a Thermo label, and therefore you can shoot it on a shorter column, so the eluting temperature is lower, and therefore the fragmentation is lower. And if you combine this here with a PTV injector, you even have the benefit of stability over the time. My colleague, he did a lot of experiments comparing this PTV injector towards the split-splitless injector. And on the longer column, you can shoot all the other congeners to get this chromatographical separation. If you drive this to extreme here, you can have two line splitter in each GC and run up to 4 columns, what the people here on this in the lab in Bavaria do. And so they cover 3 applications on one systems using 4 columns. It's for PCBs, BDEs, split again to on a short column for the 209 single, and for the rest of the BDEs, and 1 column for the dioxins. But I think you need a little experience to make this run in a routine basis. A next option which is available is the dual data option. We did some work on the hardware, and for all of you who don't know what it is simply a tool to increase productivity. Because with that option you can guide only the interesting part of a chromatogram into the mass spec. And by that you can run a staggered injection where you run both GCs at the same time, and in the end the sample throughput is a lot higher than on a regular basis. How does it work? Here, down here you have the system, 2 GCs, left GC, right GC. If you take a look inside of the GC, there's a schematic here. So on GC1 here, when there are 2 valves connected to vacuum, to helium, they are separated with a restriction. And whenever you switch those valves, or you leave those valves off, whatever comes from the analytical column will be guided into the mass spec. If you switch the valves in the on position, like shown here on the GC2, then the analytical flow is guided into the service vacuum. Now, how does it look in a sequence? Here we have the timeline, which goes over the sequence timeline, if you want. The upper part is GC1, lower part is GC2. And when I start this animation, it's probably a little quick to comment on it. So it will start with injection here on the right side. It will be blended out. And once the valves are switched, everything's guided into the mass spec. The data are acquired. In the meantime, there was an injection here, which was blended out. And therefore, there's like on a ping pong game. And if you take a closer look, you see that only one flow at a time comes to the mass spec. And by that, the DFS, which is the most expensive part of this combination here, is working all the time. And this is not new. This is not new, but what is new now, we changed the old hardware, which was physically really T-pieces, and a lot of connection can create a lot of leaks. And now we implemented a so-called multi-channel device, wafer into the GC oven, connected via stainless steel capillaries to the valves outside of the oven here. And also we changed, we use now in the helium line a three-way valve, which avoids air accumulation caused by micro leaks. And the wafer itself is tiny, like a €2 coin, and all the schematic, the restriction, also the T-pieces are implemented in this wafer. And whenever you bring that volume into the column flow, you create peak shape issues like tailing. But here the dead volume is almost zero, so you can't distinguish if it is not by the peak shape, if it is done with this chip or without. Next part will be software. As I said before, I just concentrate now on the DFS instrument software. And this is also not very new, but at least probably you've never seen it. In the instrument itself, now you can checkmark this resolution check procedure. What it does, once it is enabled here, it will perform, in the end, you're going to get a PDF report of the log and Kali masses for each MID section here. And once, and the idea is to have such a method at the beginning of a sequence and at the end of the sequence. And this is also needed for the APA method 1613. Another thing is, when you take a look here at the instrument software, you always see those readback parameters on the right-hand side. And if you take a closer look, there's one part where you can, which is called acquisition log. So if you go to this part there you can, come on. When you go to this part with the right mouse click, you can enable each of those readback parameters. And then they are displayed here, but on top of it, if you run a sequence, there will be, all those parameters will be written in the raw file itself. So later on in the qual browser, you can take a look, scan by scan, and you're gonna get those values out here. And on top of it, there will be also a file created, once again, with the same name as your raw file, with the extension ACQ, which is a simple text file. And the nice thing of this is if you import it into Excel, for example, also the acquisition time is displayed here. So later on, you can make a display of your value, graphical display here. And as an example, I choose the ion source pressure. The whole thing was designed once for troubleshooting and also for diagnosis, but you can also use it for other things. Let's say here you have the ion source pressure profile of the solvent peak, for example. And if there's something wrong with the intensity and you highlight this all the time, later on it gives you the opportunity to take a look. Maybe there was something wrong with the injection, that there was a bubble in there, and therefore then you would probably see a lower peak here. This is one thing, what you can think. Another thing is very powerful when you, for example, do a method development, like let's say like large volume PTV. The profile of the pressure tells you a lot about optimizing the method. Okay, so next thing. I thought about to bring this in or not. So far we learned how to get additional information out of the instrument. And this part here now reminds me on a poster which was at the lab in the university saying, if you can't convince them, confuse them. But no worries, I don't want to confuse you. I just want to show you that what is possible. So that that is not death so far. So the software is still open. When you take a look here at the normal software, down here there's a DC dialog. So whenever you push a button or do something, those commands, you see the commands here in the DC dialog. So that's the communication between your software and the mass spec. Okay? So and as an example, you can set, let's say, the ion source temperature to 100 degrees. And then afterwards you're going to see the command ISTS, ion source temperature setting, and the value will be 100. And you can do the same with a Lua command here on that side. You open a dialog, type it in, send it over, and then the ion source temperature will be set to 100. Once again, it's not a training course, it's just to give you an idea about how it is working. Okay, so now you can sum up multiple Lua commands into a Lua script. And as an example here, when you start a sequence, at the end of the sequence you can tell the system if it should go to standby or if it stays on or you want to switch it off. You can do the same by using a Lua script. And in the instrument itself you see this middle part here which says additional action. And there you can choose multiple Lua scripts. Okay, and in this example I choose the Lua script called standby. Okay, so you choose it, save the whole instrument method with a name, let's say standby, and then you take this method at the end of the sequence. You use, instead of your normal instrument method, you use the standby method here, which is a dummy standby. The only purpose here, or the only job of this line is to perform this script. Okay, and afterwards the instrument will be in standby. And there are lots of Lua scripts already in the system, which you find under this directory here, but they are also free editable. So you can change them with, let's say, a Notepad++, which is free software, what you can get. And if you take a look, once again, to our example, that's the script here for the standby procedure. And here you see the commands which will be performed. Let's say, accelerating voltage 0, dynode 0, multiplier 0. Now you can substitute those commands in, let's say, our command, what we learned before, the ion source temperature 100, and then you save it and you have a script that after sequence you can cool down the ion source, for example. And this is only an example. This is very, very flexible, so you can do whatever you like. You can stop a sequence or check the filament if it's still alive, or if it is dead, you stop the sequence, and so on. So that shows you that there's still a lot of possible. So it's not a closed software, okay? Okay, and finally, I want to give you an update about our timed cryogenic zoom compression project. And first of all, I want to say on our website, you can download this publication here, which describes a little bit the principle. The whole thing is so far an R&D project. We have a cooperation with CDC and also with Jeff. And the idea is, or the long-term goal is, to increase sensitivity, and we want to go into the sub-femtogram level. But this is still a long way, and I want to show you where we are right now. So far we used a hardware which was designed simply for GC times GC. But we use those GC times GC unit, only one part of it. This is a cryojet which sprays liquid CO2 to a very tiny piece, part of column. So here you have the column, that's the sprayer, and by cooling it down you can trap components in there. And right now we developed, or are in the process of developing a new hardware, and I can't say something about it because we want to make a patent out of it, but it's pretty cool. So the principle is very easy. So you leave your, let's say, 60-meter column here, and before the column reaches the mass spec, in a distance somewhere, you position the jet. And when you shoot your sample, you're going to get, sorry, oh, this was too. You're going to get the result what you're going to expect. You get a normal peak because it's one long column. But before the analyte reaches the jet here, you can freeze it, this part here, by simply switching the jet on. And then it will be refocused, because typically what you see is on a long column, the peak will be broadening, and at some point it got lost in the baseline. And with that you can refocus it, and when you release it or re-inject it to the second dimension here, you get what you're going to expect from this shorter column. You're going to get a very nice narrow peak. So you still have the chromatographical separation power, but a peak shape of a very short column. Once again here, this is an illustration how you see it on the first dimension. You have a broad peak. On the second dimension, the peak is completely trapped, re-released on the second dimension, and the peak width is very small, but the amount is the same, and therefore the peak height is higher. And in the end, you get a better signal-to-noise increase, where the gain in sensitivity is coming from. Now, here's an example, is one mass trace of the internal standard. We have the 1234 TCDD, 13C labeled, and the 2378. Both have the same instrument response. They are shot at the same time, same concentration. The only difference here is that the 2378 was cryofocused and the 1234 not. And there you see the gain in intensity, peak intensity. Here's almost, or it's 10 times more. And the idea is now, because the whole thing is time controlled, so you can really switch the jet on whenever you like or switch it off. This is controlled in the software, in the instrument method itself. It's pretty easy, controlled by the GC. And then you can say, for example, that's a full chromatogram of all the congeners here. And you say, for example, all the red ones now here are cryofocused, the PCB 77, for example, the TCDD, the 2378, PCB 126. One of the pentadioxine, and you see there are very tiny needles compared to the rest of the peaks here. And to the performance, that was an experiment. This was all done with the old hardware so far. That's an injection of different congeners here, all TCDD, one mass trace, nothing cryofocused, and but I stayed with the same intensity level here, so they are all normalized. And here in this first example, I only cryofocus the first one, 12378. The second one, in the second run, I only cryofocus this one, and that one. And then you see that the retention time of all the other congeners are not touched, so they are pretty much the same, because you don't block the helium flow, you only trap the component. And to the sensitivity, we got special certified standards and very low concentration, and we shot 4 microliters injection, and I can say down to 0.5, so 500 attogram per microliter, but 4 microliters, so in total it was 2 femtogram on column. You can make a nice calibration curve. We try to get lower, but then we're still working on it. Those are the very last experiments what I did last month at CDC in Atlanta. So we tested the new hardware, and this is an example where we tried it for the Deca, because the new hardware cools down a lot faster and more precise. And here I trapped the 209, and that is an example of their lowest standard, what they typically use. And yeah, the peak looks very ripped apart, but when you use the cryofocusing, it looks nice again. So by that, we shot a completely calibration curve and everything. So it looked, with the first try, we already can say that the limit of detection was twice as good as before. And when you take a closer look here, this is an overlay of a non-cryofocused 209 and the cryofocused one. And if you zoom into the noise level here, you see when you cryofocus, this part here is missing where the peak was before, because you cryofocused everything. So it's very precise where you're going to cut it and release it again. And with that, I would like to close. That was my last one. Yeah, thank you for your attention. Okay.